Welcome back to the deep dive. Today, we are strapping in and heading straight into the mathematical engine room of quantum mechanics. Our focus is Chapter 8 of the Feynman Lectures on Physics, Volume 3, the Hamiltonian Matrix. We've spent time defining what quantum states are, superpositions and probabilities, but today our mission is really to decode the fundamental law that tells us how those states change over time.
Yeah, this is the crucial leap, really. Describing a system at rest is one thing, but defining its motion, its dynamics, that's the essence of physics, right? Feynman introduces a robust system of matrix algebra here that provides the complete roadmap for calculating, well, every future probability and transition within a quantum system. We're moving beyond just intuition and into predictable, calculable dynamics.
So we're dealing with the language of motion, essentially. We'll start by mastering the mathematical tools, the bracket notation and states as vectors. Then we'll see how a mysterious time evolution operator inevitably simplifies into the almighty Hamiltonian matrix, which, as we'll see, contains all the physical laws of the system. Okay, let's unpack the foundational language first. Quantum states, like final angle, they're treated mathematically like vectors, but operating in a complex space. The single most important concept seems to be the transition amplitude. The probability, or rather the amplitude, of finding a system that started in state final in some other state final.
Exactly. And to compute that amplitude, we use the genius of Dirac's notation, the bracket, or bracket, written as l'angle chi-fine angle.
Yeah.
Think back to classical mechanics. If you want to find the overlap or relationship between two ordinary vectors, you use the dot product, right? And that gives you a single scalar number.
Right. But why do we need two different parts here, the bra and the gut, if we're just defining a state as a vector? What precisely is the mathematical role of the bra, l'angle chi-ket?
That's a fantastic question because it really highlights why complex numbers are so essential in quantum mechanics. The bra, triangle, that's the state vector itself. You can think of it like a column vector. The bra, l'angle chi, is its necessary partner. Mathematically, the bra is the complex conjugate transpose of its corresponding car.
Okay, complex conjugate transpose.
Yeah, it essentially takes the state vector, flips it into a row vector, and takes the complex conjugate of each element. It gets it ready to interact with the bra. When they come together in the bracket, l'angle chi wrangle, they perform an operation very similar to a dot product, but adapted for complex vectors, and compute that single vital complex number, the probability amplitude.
Got it. So without the bra representing that conjugate transpose, the math just wouldn't give us probabilities that make sense physically.
Precisely. It wouldn't work.
That vector analogy is powerful because it gives us an immediate way to sort of decompose any quantum state. We can express any arbitrary state as a superposition of known, distinct possibilities, which Feynman calls base states.
Exactly. If we define a complete set of base states, I-wrangle, then any state triangle can be written as a linear combination of those base states. The complex coefficient in front of each base state, which we write as a chi-wrangle, is actually calculated by Lange-Lange wrangle. That sickle is the amplitude of finding the system in that specific possibility, defin.
And this leads us to a really fundamental mathematical simplification, orthogonality. The base states must be orthogonal. Why does that matter so much for the math?
Well, orthogonality means that the amplitude for a base state wrangle to be found in any other distinct base state wrangle dollar is exactly 0. So Langle-Wrangle even dollar is not equal to 0.
Okay.
Think about it. If your base states were not orthogonal, if they sort of overlapped or weren't entirely independent, calculating those coefficients, Styler would become incredibly messy. Every base state would kind of bleed into the others mathematically. Orthogonality simplifies the whole complex system into these distinct, manageable components. It's crucial.
Right. So moving from the abstract math to physical reality, we have this elegant algebraic framework. But what physically are these base states? What defines a complete description of the world?
And that's a key question. The choice of base states depends entirely on what physical properties you need to specify to completely differentiate one possibility from another within the system you're observing. You have to define a complete set of possibilities.
Let's take the example Feynman uses, a simple electron. If we only described its momentum, that wouldn't be a complete base state, would it?
No, definitely not, because an electron also has this intrinsic property called spin. So a single complete base state dollar wrangle for an electron must encode definite simultaneous values for all its relevant properties, its specific momentum, and whether its spin is pointing up or down relative to some axis.
I see.
If you just ignore spin, well, your math won't reflect reality. You haven't fully defined the state.
So an electron with momentum p dollar and spin up is one base state. And an electron with the same momentum p dollars but spin down is a completely separate orthogonal base state.
That's exactly correct. Even though the momentum is the same, the different spin makes it a distinct orthogonal possibility. Now, imagine scaling up to a more complex system, like, say, a hydrogen atom that's a proton and an electron interacting. The complexity of defining a complete base state just explodes.
Right, because you'd need to specify.
Well, you'd have to define the spin state of the proton, the spin state of the electron, the momentum of both particles, maybe their relative position or internal energy state. It gets very complicated very fast. The key takeaway for you, the listener, is that a full description of even a small piece of nature requires defining potentially a massive, often infinite number of these distinct base states. They are the scaffolding, really, upon which all quantum calculations rest.
Okay, so we know how to freeze the system, describe its state at time t dollars, but, nothing in the universe is static. How do we introduce time? How do we describe how a state evolves from time $2 to time $2?
That transition, that evolution, is governed by what we call the time evolution amplitude, or sometimes just the dollar operator, often written as UT2, T1 Mathematically, it's the operator that takes the initial state vector at $1 and transforms it, or maps it, onto the final state vector at T2. So UTT2 $1.
So that dollar operator, covering a macroscopic period of time, could be incredibly complex to figure out directly. How does Feynman recommend we actually handle this full-time evolution?
We use the classic trick from calculus. We break the whole evolution down into infinitesimally small, tiny steps. Let's call the duration delta t dollar. If the time step delta 2 is really, really small, then the state vector at time plus delta 2 should be very, very similar to the state vector at time t dollars.
That's right, makes sense.
This similarity allows us to relate the rate of change of the probability amplitudes, the $6, back to the state at time t dollars.
Wait a minute, if we break down the evolution into tiny time steps and look at the rate of change, that sounds like we're heading straight toward a differential equation structure. Isn't that the definition of dynamics in physics?
Exactly. You've hit it. That's the critical pivot in this chapter. Analyzing that infinitesimal change mathematically forces us into a differential equation setup. What you find is that the rate of change of the amplitude to be in base state dollars, depends linearly on all the other amplitudes c to dollars in the system at that moment. And the coefficients that determine how strongly each c to dollar influences the change in CL, those coefficients form a matrix. And that matrix is the famous dollar matrix.
Ah, okay. So this is where the mathematical structure truly connects to the physics. These coefficients in those coupled differential equations are the elements of the Hamiltonian matrix. What physical information does that matrix element actually carry? What does it represent?
This is really the crux of the whole chapter. J is the energy matrix element. More specifically, it represents the coupling or the interaction energy that allows or drives the system to transition from base state Eridal to base state Wrangle.
So if it is zero?
If A is zero, there's no physical mechanism connecting those two states. There's no interaction pathway, and a direct transition between them is impossible, at least according to the physics described by this Hamiltonian. The Hamiltonian matrix, dollars, contains all the information about the system's internal physics, the forces, the interactions, any external fields, the potential energies. It's all packed into those numbers.
If we connect this back to classical mechanics, remember the Hamiltonian function describes the total energy and basically dictates the motion of a system. So this quantum mechanical dollar matrix serves the exact same role.
That's absolutely the right connection to make. It plays the same fundamental role, but it operates on these abstract state vectors in Hilbert space, rather than on classical positions and momenta. And because this matrix defines physical reality, it has to obey a really crucial mathematical rule. Feynman emphasizes this strongly. The dollar matrix must be Hermitian.
Hermitian. Okay, why is that property where high G equals the complex conjugate of TT, why is that so fundamentally important in quantum mechanics?
It's the mathematical guarantee of probability conservation. We often call it unitarity in the context of the time evolution operator for dollar. When the Hamiltonian dollar is Hermitian, it ensures that the time evolution operator to dollar that it generates preserves the total magnitude or norm of the state vector.
Okay, and in plain language, what does preserving the norm mean?
It means that the total probability of finding the particle somewhere, which is the sum of the absolute squares of all the amplitudes, some CIT22, always remains exactly equal to 1. If dollar were not Hermitian, then as time went on, this total probability could drift away from 1. It might become greater than 1 or less than 1, which is physically impossible.
Right, because the particle has to be somewhere.
Exactly. The Hermitian property keeps reality consistent. It ensures probability makes sense over time.
So the whole derivation, starting from tiny time steps, incorporating the physics into IJ, and constrained by this essential Hermitian property, it culminates in the complete quantum mechanical law for how probability amplitudes evolve over time. And that equation is,
I bar a C ni Cj T, where no bar is the reduced Planck constant.
right, this is it, the mathematical definition of quantum dynamics. It tells us that the rate of change of the amplitude for state dollar depends on the energy coupling to all other possible states, weighted by their current amplitude.
It's an incredibly dense and elegant summation of physics, isn't it? And the real power of this framework, I think, is best seen when we apply it to a simple, solvable physical system.
Okay, let's definitely do that. Let's make this concrete with the ammonia molecule text NH33. Feynman uses this as the perfect example of a two-state system.
Right. So picture the ammonia molecule. It looks kind of like a little pyramid. You have the 3 hydrogen atoms forming a flat triangle base, and then the nitrogen atom sits either above that plane.
Let's call that state $1.
Okay, state $1 rebel. Or the nitrogen atom could be sitting below the plane of hydrogens.
State $2.
State $2 angle. And because these two positions are physically equivalent due to symmetry, this naturally forms a beautiful, simplified two-state system governed by just a $2 times 22 Hamiltonian matrix.
Okay, so for a $2 times Q2 matrix, we need 4 elements, H times $22 and H $21. What can we say about them?
Well, because of that symmetry we mentioned, the energy of the molecule should be the same, whether the nitrogen is definitively in state $1 angle or definitively in state 2 angles. So the diagonal elements must be equal. Let's call them H12IU, E2000, E dollars.
Okay, $E is like the base energy if the nitrogen were just stuck in one position.
Exactly. Now consider the off-diagonal elements, H12 and H21s. These represent the coupling, the possibility of transition between state 2 and state 1 and state 1 and state 2, respectively. If the nitrogen were just a classical ball separated from the other side by a potential energy barrier created by the hydrogens, it couldn't get across without enough energy. In that classical view, those off-diagonal elements, H12 and H21 as well, would just be 0.
Meaning no transition is possible. The nitrogen would just stay put wherever it started.
Right. But because it's a quantum system, the H12 and H20 elements are not 0. Due to the Hermitian requirement, they must be complex conjugates, and in this symmetric case, they turn out to be equal and real. Let's call them H12, H21, where $1 is some positive constant representing the strength of the coupling.
Okay, so there is a connection. What's the physical mechanism that creates this non-zero transition amplitude, this dilatal?
The mechanism is pure quantum mechanics. It's tunneling.
Ah, tunneling.
Yeah. The nitrogen atom doesn't need enough energy to classically climb over the potential energy barrier presented by the hydrogen plane. It has a certain probability amplitude to just tunnel right through it. This non-zero transition amplitude essentially dictates the rate at which the system can flip between state $1 angle and state $2 angle. So rather, there's that interaction energy element, the H12 coupling, that makes the system dynamic and interesting.
Okay, so we have our simple $2 times 2 Hamiltonian matrix, HD dollars, H20 I.
Right.
We plug this into that master quantum dynamic equation, high bar, Ferquhar D, CIT, TG8. What does the resulting solution tell us about the molecule's behavior over time?
It tells us something really fascinating. Oscillation. Let's say the molecule starts definitively in state $1 angle at time $2 $1. So C1, OMR $1, and AC2 $1. When you solve the coupled differential equations with this Hamiltonian, the solution shows that the probability of finding it in state $1 angle, which is C $hun T2, decreases over time, while the probability of finding it in state $2 angle ion increases.
So it starts to flip.
Exactly. And then the process reverses. The probabilities oscillate back and forth sinusoidally. The molecule literally flips between the nitrogen up state and the nitrogen down state, passing through the hydrogen plane via tunneling.
Wow. And this flipping is the observable behavior, and it's a direct consequence of the energy structure defined by that simple dollar matrix, particularly the non-zero tunneling term, Auton.
Absolutely. The very existence of that tunneling amplitude $1 fundamentally changes the energy landscape. The system no longer has just one possible energy, E dollars. Instead, the mathematical structure of the Hamiltonian, when you find its stationary states or energy eigenstates, reveals that the system has two distinct, definite energy levels. One slightly higher at $t plus eta, and one slightly lower at T's dollars.
An energy splitting.
Yes, an energy splitting. And the frequency of that observable oscillation, the rate at which the nitrogen flips back and forth, is determined precisely by the difference between these two energy states, which is E0 plus A, E0 eta A equals 2A. It's proportional to A Bogoer. This energy splitting, caused directly by the quantum possibility of tunneling, is the key quantum mechanical reason for the observed behavior of the ammonia molecule, which was famously used in early masers. The matrix algebra perfectly dictates both the possible energies and the time evolution. So what does this all mean for you, listening? The immense power contained within this chapter, chapter 8, is the realization that these complex, often counterintuitive quantum phenomena, like a molecule tunneling through a solid energy barrier, are perfectly and predictably governed by the straightforward rules of linear algebra and matrices. Provided, of course, we correctly identify and quantify the energy couplings, those IA elements that represent the underlying physics, the physical laws are entirely contained within the structure of that Hamiltonian matrix.
Yeah, the big takeaway for me is seeing how the evolution of any quantum state over time, which is arguably the most fundamental dynamic law in the universe, is elegantly encoded entirely within the structure, especially the Hermitian structure, of this thing called the Hamiltonian matrix. It truly is the master equation, the engine of the quantum world. Well, thank you for joining us for this deep dive into the language of quantum dynamics. It's certainly a lot to digest.
It definitely is. And maybe here's a final thought for you to mull over as you go. If the Hamiltonian matrix truly contains all the physical laws governing a system, and the physical laws determine everything that can possibly happen, what does that imply about the ultimate human endeavor to perhaps one day determine the complete Hamiltonian matrix for the entire universe? If we knew that ultimate matrix, every single dollar for everything, would we, in principle, be able to predict absolutely everything that happens? Something to think about.